Then we'll see in the next slide how can we enforce the coherence on the memory system, or what are the methods used for enforcing coherence. So coherent caches provide migration and replication of the shared data. Coherent cache can provide migration and replication of shared data. So what do you mean by replication? From the name itself, you will get the idea. You are replicating the copy of the data, or you are duplicating the copy of the data. So the same data can be replicated in multiple private caches. We have already seen in one of the slide. The same data will be available in private cache of core 3, as well as it may be available in private cache of core 1, for example. The same data will be replicated in multiple private caches. So when one cache is updated, all the other copies should be either invalidated or updated. So if you are updating one cache copy, all the other copies of the same data should be either invalidated or updated. So what do you mean by invalidation and updation? These are the two methods used for updating a particular location. So for that there are two particular protocols are there, known as cache invalidation protocol and cache updation protocol. So that we will see in the forthcoming slides. So now we need to understand that when you are trying to update one of the cache data, whichever copies of the same data is present in the other private caches, those copies will be either invalidated or updated based on the cache coherence protocol what you are having. Generally, there are two cache coherence protocol, that is cache invalidation protocol and cache updation protocol, that we will see in the next slide. So what do you mean by migration? If one core, that is core 2, need a data present in the cache memory of another core known as say P1, one of the method is whole block of data that is requested by P2 can be migrated from cache of P1 to cache of P2. The block of data will be migrated from the private cache of P1 to the private cache of P2. That method is known as migration. So what is the advantage of that? Only one copy of data will be preserved. So if the cache memory is using replication method, more than one copy of data will be there, and whenever you are updating one copy, all the other copies will be either updated or invalidated based on the cache coherency protocol, whether you are using cache invalidation protocol or cache updation protocol. Right. Then another method is, if you want to have only one copy of data present in a location, if you don't want multiple copies, what you need to do? You need to perform migration technique. So if one core is trying to read the data which is present in another core, what will happen? The data present in the second core will be migrated to the first core. Right. In this case, data present in P1 will be migrated to the cache of P2. So only one copy of data will be maintained. Then we will see what are the different types of protocols generally used in cache coherency. So I have already told there are two types of protocol. One is known as write invalidation protocol. Another one is write updation protocol. Two types of generally used protocols are there, right? So we are having two types of protocol. One is known as write invalidation and write update protocol. We are also having two types of cache memory. We have seen last class. One is known as write through cache and write back cache. What is the advantage of write through cache? When you are updating one copy, all the other data present in the other levels of memory will get automatically updated in write through cache. In write back cache, when you are writing one copy of data, the other copy of data present in the lower levels will be updated only when the data present in first level is removed or evicted. Right. So these are the two types of caches. These are the two types of protocols available. So since we are having these two categories, The cache coherence protocol design space consists of 4 protocol types. The cache coherency protocol design space consists of 4 protocols. What are they? One is write through cache with write invalidation protocol. Another one is write through cache with write update protocol. Similarly, the third type of protocol design is write back cache with write invalidation protocol and write back cache with write update protocol. So since we are having 2 types of memory and 2 types of protocol design, we can have 4 types of coherence protocol design. One is write through cache with the write invalidation protocol. Second one is write through cache with the write update protocol. Similarly, write back cache with the write invalidation and write back cache with write update protocol. So next we will see what do you mean by write invalidation protocol. So from the name itself we will get some idea that something will be invalidated. Right, some of the memory location will be invalidated. Invalidation means disabled. It is something like disabled. It is the opposite of validation. Invalidating means you are disabling a memory block from so that the other cores or other cache memory cannot access that block once it is invalidated. So we are preventing other blocks from accessing this data by making it invalidated. Right. So whenever a processor core need to write a data to its cache, its private cache, what will happen? It invalidates all the other replicated copies of that same data present on other processors. So based on the if we are using write invalidation protocol, what is happening? Whenever the processor core need to write the data to its private cache, what will happen? If there are multiple replicated copies of that same data present in other processes, all those replicated copies will be invalidated. So what is the advantage of that? Only one copy of data will be preserved at a particular point of time. Right. So whenever the processor is writing or updating the data present in its private cache, all the other copies of the same data which is present in the other processes will get invalidated or disabled. So how it is done? By sending an invalidation signal to all the other cores. So the processor which is going to write the data to its private cache will send a signal known as invalidation signal to all the other cores and inform that I am going to write the data into my cache. So all the other copies of the same data should be invalidated. So what is the invalidation signal consists of? The invalidation signal consists of address of the block of data where the write will be performed. So what do you mean by an invalidation signal? Invalidation signal is nothing but address of the block of data where the first processor was going to write the data in its private cache. Right. So the same address where the processor is going to write the data, that address will be sent as an invalidation signal to all the other cores. So the same address will be sent to all the other cores. So what will the other cores do? The cache controller associated with those caches present in other cores, right? Because each of the core is having private cache and these private caches are controlled by corresponding cache controller. All the caches will be having cache controller which is taking care of the write or read process on the cache. So the cache controller associated with those private cache of other process, what does it do? It will search for the address in their cache. So whenever a processor is sending an address of block to other process where the write has done, what does the cache controller of other processor do? It will read the address, right? Because all the cache controllers will be getting the same address, what is transmitted by the processor core. Because generally it is connected in a bus. We have seen in the last class. All the cores are connected to a single bus. So if one processor is sending an invalidation signal or the address of the block of data, all the other private caches will be receiving that. So what will the other private caches do? The cache controller present in that cache will read the address and search for the address in their associated cache. So it will take the address and check whether that address is present in their cache, their private cache. And if the cache controller is finding a match, that means if the cache controller identifies that the address is present there, what does it do? That particular block with the particular address will be invalidated or disabled. So whenever the cache controller identifies that the particular address sent by the first processor is present in its own private cache, what does it do? That block will be invalidated. So by doing this invalidation, what we are expecting? We ensures that only one copy of data is present for write operation. Right. So whenever the processor is trying to write the data to a particular address location in its cache, that address location will be sent through the bus to all the processors. So whatever so the cache controllers associated with that processor will read this address and check whether that address is present in their own private cache. If that address is matching, what does it do? The cache controller will invalidate that block or disable the block from next write process or read process. So that we are ensuring that only one copy of data is available for the write operation. This is known as write invalidation protocol. So what are the merits and demerits of write invalidation protocol? Demerit is that if these invalidated blocks, because we have invalidated certain blocks of memory present in various other processes, if these invalidated blocks are required by their own cores, because we have invalidated the block of address location, the address location present in other private cache memory. So if the corresponding core need to access the same blocks which are invalidated, what will happen? That core will not be able to access the data because it is invalidated. So what will happen? Cache miss will happen. Say if I have, for example, if I have invalidated, say address location D present in core 4. I have invalidated address location D in core 4. But after some time, core 4 is trying to access the data from D, same invalidated location D. So what will happen? The core will not be able to get the data from D. Why? Because D is invalidated by the cache controller. So what will happen? Cache miss will occur because the data is not, the processor was the core was not able to take the data from the cache. So cache miss will happen, then it should go to a shared memory or to the memory to access the data. So if these invalidated blocks are required by the core, then cache miss rate will be increased. Cache miss rate will be increased because those blocks are invalidated. So this is one of the demerit of write invalidation protocol. Then what are the merits? Since only the address of the block is sent through the bus bandwidth will not be affected too much. Because the invalidation signal, what I told here was, what was that? Only the address of the block of data that is being written will be sent through the bus to the other process. So only the address is sent. So the bus bandwidth will not be affected too much because only the address will be sent. That is the first merit. Second merit is, since unnecessary writes are blocked, power consumption will be reduced. Because we are trying to write the data only to one location. Other locations we are invalidating. We are not allowing the write to happen in other locations. So since unnecessary writes are blocked, power consumption will be reduced. So these are the merits and demerits of write invalidation protocol. Next type of cache coherency protocol is write update protocol. So from the name itself, you will get some idea that updation of data will be present. So how it is done? When a processor need to write the data, what it will do? It will send an update request to all the other processor cores. But in the previous write invalidation protocol, what was done? When a processor need to write the data, it will send invalidation request to all the other processor core, so that all the other blocks of memory present in other cores which is having same data will be invalidated. But here, since when the processor need to write the data, it will send an update request to all the cores. Right. That means if you are updating one copy, all the other copies will get updated. Right. So the address along with the data has to be sent through the bus for store operation. Write means store operation. Right. So here, since all the copies of data should be updated with the new data, what all things has to be sent through the bus? Address along with the data should be sent. But in write invalidation protocol, only the address need to be sent, because whichever, if this address is present in other cores, those address location need to be disabled. But here, since we need to update the data, if the same address is present in other cores, what all things has to be sent? Address as well as data has to be sent to all the cores. So since address and data you are sending, bandwidth will be, more bandwidth will be used. So the bandwidth of bus will be affected. So the cache controller associated with other cores, what does it do? When it is getting this address and data, it will search for the match as it was done in the invalidation protocol. Right? The cache controller will read the address. It will check whether that address is present in their private cache. If the address is present, what will happen? The data will be updated in the associated private cache. Say for example, P1 is trying to write a data to D as 5. So what does P1 do? P1 will send the address location D as well as the data, that is 5, to all the cores. So the cache controller associated with each of the core will read the address and the data from the bus, and if the address is matching with the address present in their private cache, say for example P3 is having the same address location, so the cache controller will read the data, read the address, and if the address is present in P3, what does it do? It will update the cache with the new data. Right? So what is the advantage? It will ensure that all the copies of data will be updated if the data is available in their respective caches. Right? If the data is available in the respective caches. If the data is not available, it won't be updated. So it ensures that all the copies of same data present in the same address location of all the processes will get updated. So what are the merits and demerits of write update protocol? This is a merit. If these replicated blocks are required by their own core, then cache miss won't happen. Right. In the invalidation protocol, we have seen that since the address location is invalidated, and if core is trying to access the same data, cache miss will happen. But here, since we are updating all the data present in all the cores, right? If the same data is present in multiple cores, all that copies of the same data will be updated. So what is the advantage? If the core is trying to get the same data present in their own private cache, it can read from the cache. So cache miss will not happen. That is advantage. Cache miss won't happen because the data is available. We are not invalidating. We have updated the data. Then what are the disadvantages? If none of the cores needs the data, if the core need the data, then cache miss won't happen. But if none of the core need the data, then what has happened? We have made unnecessary writes and power consumption will be increased. if other cores don't need the data, but again, since we are updating all the copies of the same data present in several cores, by performing this unnecessary write of the data in all the cores, we are increasing the overall power consumption. That is the first disadvantage. Second disadvantage is, since we are sending both the address and data in the bus, here we have seen, since we are sending both the address and data in the bus bandwidth will be utilized more. In the previous case, you are sending only the address, so only the few bus bandwidth will be used, little of the bus bandwidth will be used. But here, since both address and data, more bus bandwidth will be utilized. These are the two disadvantages and advantages of write update protocol. So next, there are two more type of protocol which will be implemented based on the number of cores present in the system. Previous two protocols are the actual type of protocol. These are the two protocols which are implemented in multi-core system based on the number of cores. Right. So the underlying cache coherency protocol remains the same, that is invalidation or updation protocol. But based on the number of cores, the method of the reading the data and the address will be slightly different. So if the number of cores are 4 or 8, then the cores need to be connected through a bus. In the case of Snoop based coherence protocol. So Snoop based coherence protocol will be used when the number of core is 4 or 8. Right. So when the number of core is very limited, then all the cores will be connected through the bus, as you have seen in the previous slides. And if you want to perform read or write, the read or write request will be sent on to the bus, so that all the other cores can read from the bus. So each cache controller will be snooping on the bus. Since it is snooping on the bus, this protocol is known as Snoop-based protocol. So all the write and read requests will be sent on to the bus, and the cache controller present in each private cache will snoop on the bus. Snoop or sniff, it is almost similar. So it will be snooping on the bus and it will take the request, right? Or it will take the address. Then, as you have seen in the previous case, it will be searching for the address in their cache. If it is matching, data will be either invalidated or updated based on the previous two protocols what it is used. So when the number of cores is 4 or 8, bus connection will be there and the cache controller will be snooping on the bus. Right, it will be snooping only on the bus. Then it will take the request, it will take the address, it will check for the address whether it is matching in their private cache. If match is there, it will be either invalidated or updated. So the cache coherence protocol will be either invalidation or updation protocol. But based on the number of protocol, the cache controller will be either snooping or it will be having another technique known as directory based protocol. So if the number of cores are large, that is 16, 32, etc., instead of Snoop based coherence protocol, directory based protocol will be used. Directory based. So from the name itself, we will get the idea that one directory will be kept along with the caches. So here, instead of the bus connection, processors will be cores will be connected in a mesh topology. Since the number of cores are more, bus connection will not be there. It will be connected in a mesh topology. And in directory based protocol, it will maintain a directory for each of the caches, and shared memory will maintain the sharer information which tells which private cache is having the copy of the requested block. What does it mean? The sharer information of each block. Sharer, what do you mean by sharer information of a block? which all processors are having the same copy of the block. That is known as a sharer information or sharers information. The sharer information or sharers information of a block. What do you mean by that? Which all processors are having the same copy of the block, copy of the same block. Right. So the sharers information of the block will be present in the shared cache so that the block can be replicated in the private cache of other cores. So the sharers information of each block will be present in the shared cache. What is the advantage of that? That is known as a directory. The sharers information will be of each block will be present in the shared cache. That is known as the actual directory. So by using this directory, we can identify who all are sharing the blocks. Who all are sharing the blocks? Which all cores are sharing the same block. So what is the advantage of that? Whenever a write or read has to be performed, we already know that to which processor invalidation signal should be sent. Right. So what is the advantage of directory? What do you mean by directory? Directory contains the sharers information of each block, and this directory will be present in the shared cache. So what is the advantage of that? We can identify which all processors are sharing the same block or which all processors are having the same copy of the block. So what is the advantage of that? Again, what is the advantage? When we are trying to write or read the data to that block, we already know that to which processors, which cores the invalidation signal should be sent. Because say, for example, you are going to write a data to a block with address D. Let us take core P3 and P4 is having same D. P1 is trying to write the data to D. P3 and P4 is having the same copy. So when P1 is trying to write the data to D, we already know that P3 and P4 is having the same copy of the block. How? It is available in the directory. So in the directory, it will be already mentioned that the block D is shared by P3 and P4. So whenever P1 need to write a data to D, P1 know that invalidation signal should be sent to P3 and P4. So that is the advantage of directory based protocol, and this will be used only when the number of cores are larger. Then the directory based protocol can also be implemented in a centralized cache or a distributed cache design. So the directory can be kept as in a centralized manner or it can be distributed across the cache. If it is kept in a centralized manner, more requests need to be serviced, so the bandwidth will be utilized more or more ports has to be there. But if it is in a distributed manner, number of ports can be reduced, bandwidth utilization will be lesser. So these are the two types of protocol which we can select based on the number of cores. Then let us see one example of the cache coherence protocol implementation. So this example we have already seen. We are having 4 cores, 4 associated private caches are there, and we are having a shared cache which is again shared with the main memory and which is again connected with the main memory and IO system. So what is the addition we have made in this block diagram? We have added one table for each private cache. What does this table contain? This table contains an n-bit coherent state of each of the blocks present in the associated private cache. Let us take in this private cache of core 1, 10 blocks are there. Right. So each block will be having an associated coherent states. What are those states? Example for the coherent states are invalid, shared, modified, exclusive, etc. So based on the protocol what we are using for designing the cache coherency, there are various types of various states available in the cache coherency protocol. So if you are using a two-state cache coherency protocol, how many states will be there? Only two states will be there. If we are using three-state cache coherency protocol, three states will be there, right? That states can be, say, invalid, shared, or say exclusive. So if we are using a coherence protocol which is having two states, each block can be in either of these two states. If we are having a coherence protocol design where three states are there, then what will happen? Each of the block present in each of the private caches can have any of these three states, right? So how will you identify that that particular block of data is present, is having this state? That is present, that can be read from this table known as n-bit coherence status table, right? So if you are having 10 blocks, 10 entries will be there in this table. And what will be each entry specifying? Each entry specifies the n-bit coherent state of one block. So similarly, the state of each blocks will be present in this table. So if you are having 10 blocks, this table will be having 10 entry. So similarly, for each cache, this table will be there. So what does the table specify? It specifies the state or coherence state of that block. So if you are having three-state coherence protocol, each of the blocks can have three states. For example, say invalid state, shared state, or exclusive state. So how will you identify that which block is present in which state? You can read from this table. So actually based on the table or based on the state of a block, the action will be taken while we are reading or writing from a processor, right? So when a core 1 is trying to read from a block of data, based on which state that block is present in, the action will be performed. Either the state will be changed to a next state or the state will be maintained. Those details we will see when we are dealing with the cache coherence protocol design, right? So how the states are changing. So when a processor, when a core is reading from a block which is in say invalid state, what state change will happen? That we will see in the coherence protocol design class in the next one or two classes. So now you understand that each private cache will be having its own table which holds the coherent state of each separate blocks present in the private cache. So the state information, that is n-bit state information. So if you are having a three-state coherence design, three states will be there. If you are having four-state coherence design, four states will be there. So if you are having four states, how many bits are required for representing four states? 2 bits. If you are having only two states, how many bits are required? Only 1 bit. So that is known as n-bit state information of all associated blocks is stored in each private cache. So the state can be either invalid, shared, modified, exclusive, etc. Right. So this is how a basic cache coherence implementation is done. Next, we will take an example for a write-through cache with an invalidation protocol. Right. We have seen different types of caches and different protocols. So we'll take one example. One example we'll see with the write-through cache having cache invalidation protocol. So we'll take the same example what you have seen in one of the slides. 3 cores are there. 3 private caches are there. Core 1 is trying to read the data from its private cache, but the data was not available here. So cache miss will happen. So core 1 will try to read from the memory. In memory data was there. So that data will be read and kept it in the private cache of core 1. Similarly, core 3 is also trying to read the data, but data is not available here. So it will read the data from the memory. So core 3 private cache is having D equal to 5. Then core 3 is trying to update the data present in its private cache from D equal to 5 to D equal to 7. So what will happen? the data will be updated to D equal to 7. Then in this example, we have taken cache invalidation protocol. So what you should perform, what it should perform, all the other copies of same data should be invalidated. In cache invalidation protocol, all the other copies of the same data should be invalidated. So previously the data was 5. So where are the same data present? The same data is present in memory as well as in private cache of core 1. So according to the cache invalidation protocol, all the other copies should be invalidated once the updation of one of the copies is performed. So both the memory, the data present in memory will be invalidated as well as data present in the private cache of core 1 also will be invalidated. So once core 3 has updated the data in private cache, wherever the same copy is there, those copies will be invalidated or disabled. Then since we are having write through cache, so that is previously we have seen cache invalidation protocol present in the example. Then we will see we are having write through cache in the same example. So since we are using write through cache, what is the speciality? Write to one level will update the data in other levels also. Write to one level will update the data in other levels also. So here we have written the data to level 1 of core 3. So the lower level, that is L2 cache, that is L2, that is a memory. So if the data was present here, that data also will be updated. So what will happen? Since you are using write through cache, the data present in L2, that is a memory, right? When you have updated in L1, the same updation will happen in the next lower level in hierarchy. So here the memory is present in L2 level. So that also will be updated. So both the private cache data and the memory will be updated. Why? Because we are using write through cache. Then in the next case, core 1 is trying to read the data from its private cache. Core 1 is trying to read the data. But what happens? The data has been invalidated. That means the data is disabled. We cannot read. So since the data present in private cache of core 1 is invalidated, cache miss will happen. So when core 1 is reading, cache miss will happen because data is not there. So what will happen? Core 1 will read from the memory. Core 1 will read from the memory. And in memory, the data present is updated, that is 7. So what will core 1 get? Core 1 will get the updated data because it has read it from the memory. When it was trying to read from private cache, it was disabled or invalidated. So it will read from memory, then it will get the updated data. So it is getting the updated data. There is no problem. Similarly, core 2 is trying to read the data from the private cache. So when it is trying to read the data from private cache, in the private cache it is not there. So cache miss will happen. So it will read from the memory. So since it is reading from the memory from the same location, in memory what was the data? Data is updated to 7. So what will core 2 get? The updated data 7. So since there is no data in private cache of core 2, D will be read from the memory. In the memory, it is having 7 as the data. So core 3 will be getting 7 itself. So what we have achieved? We have achieved cache coherency. What do you mean by cache coherency? Whenever a core is reading the data, it should get the recently updated data. Right? What was the cache coherency problem? When core 1 and core 2 was reading, what was happening? It was getting only the old data, that is D equal to 5. But here by incorporating cache invalidation protocol in the write through cache, we have overcome the cache coherency protocol and cache coherency was achieved. Why it was achieved? Because when core 1 and core 2 was reading, it was able to get the recently updated data. So this is an example showing the Cache Coherency Protocol implementation.